This is 4.2, number 61. They want regions of concave up, regions of concave down, and inflection points. So first thing, you have to know that the areas or the points where they can change concave up to concave down and vice versa are where the second derivative is 0 or the second derivative does not exist. Don't call those critical points. Critical points where the first derivative is 0 or the first derivative does not exist. So be careful about your terminology. You could say critical points of the first derivative, speaking of the second, but just be careful. All right, to take the derivative, I have a product rule. I leave the first alone, and I take the derivative of the second. Then I take the derivative of the first and leave the second alone. I am going to factor out e to the x to make it prettier, because you should see that they both have an e to the x. So if I take that out, I'm left with a 1 plus x minus 3, which is e to the x, x minus 2, I hope. And then we have to take the derivative again, and it's going to be the product rule again. I leave the first alone, and I take the derivative of the second. And then I take the derivative of the first and leave the second alone. And then you'll notice they both have an e to the x again. And so the second derivative, I factor out that e to the x, I'm left with a 1 and an x minus 2. So what do we get? We get e to the x, x minus 1. Interesting. I will box those so we can see that. All right. Not so bad. Then the question is, when does this equal 0 and when is this undefined? So we set this equal to 0 and we set each factor equal to 0. And the first question, when does that equal 0? And this comes back to, and eventually you're going to see this if you're not seeing it now. You need to know the graph of e to the x looks like this. And if you want to know when it equals 0, in other words, when does it cross the x-axis? It never does. When a function crosses the x-axis, that's when it equals 0. But since it never crosses the x-axis, this never equals 0. So that has no solution. And then this. So what have we learned? There's only one possible place where concavity can change. And how do we find out? We make a number line data table. This is 1, this is x, this is f double prime. Why double prime? Because we're looking at concavity. So obviously we look at double prime. Pick a number to the left, pick a number to the right. Now, as I was looking at your homework, there were quite a few people that didn't make any tables, never tested any points, yet they had answers. You need to show your work of where these answers come from. So I need to see a table or a testing of points. So plug in 0 into the second derivative because you want to know if it's concave up or down, and you should know that justification is the second derivative. All right, we have a quiz tomorrow. These are things you should know. All right, e to the 0 is 1, and 0 minus 1 is negative 1. So a positive times a negative is going to be negative. So the second derivative is negative everywhere to the left of 1. Because it can only change signs at 1. So therefore, it's always negative to the left of 1. This will be negative infinity to infinity, by the way. Plug in 2. E squared is positive. 2 minus 1 is positive. A positive times a positive is always positive. So our conclusion, F, is concave down, where? On the interval from negative infinity to 1. Why? Because f double prime is negative on the interval from negative infinity to 1. That's your justification for concave down. When you do FRQs, you can't just put an answer. You got to give a reason why. It's because the second derivative is negative. You could put -1, -5, and the reason is because anywhere between, the only place where it can change signs is at 1. So therefore, it's either always positive or always negative to the left. So any point you pick is going to get the same sign. It's not going to change, okay? Then we say, I'm going to copy and paste because I don't want to write all this stuff down again, and only a couple things are going to change. So I'm going to copy and paste this. And the other reason it's going to be, the other region that was going to be concave up. So I'm going to erase that, put up, and it's concave up from 1 to infinity. So I'm going to change that interval from 1 to infinity. And the reason the second derivative is positive on that region, you'll see it's positive everywhere from 1 to infinity. So we say the second derivative is positive, and the region is from 1 to infinity. So that would be the regions of concave up, the regions of concave down, and the justification with it. Now, the last thing they ask for inflection points. Inflection points occur when the second derivative changes signs, and it changes signs at 1. It went from negative to positive. So I would say F has an inflection point. Whoa, I ran out of room. Lame-o was his name-o. Inflection. Whoops, that's an L, not a T. Inflection point at x equals 1. What's the reason? Because F double prime changes signs at x equals 1. Done. That is how you find regions of concave up, concave down, and inflection